Hi, in this video we'll be looking at our 2271's tutorial 5 suggested solutions. Okay, so the first part of the tutorial is focusing on the topic on scheduling. Okay, so basically what is scheduling? It is the ability to look at multiple tasks, okay, and try to think or analyze the best possible way they should be scheduled, okay, based on different scheduling strategies, okay, that we will be discussing, that we have seen in the lecture slides. Okay, of course we are making some assumptions here, which may not always hold true in some cases. We are making an assumption that at time t equals to 0 is where all the tasks are available, mhm, which may not always hold true. Okay, and we are also making an assumption that tasks are periodic in nature. Okay, so some tasks may be periodic, some tasks may be aperiodic. Okay, so for the analysis part we are making some assumptions, okay, but in reality, as you are seeing in your mini project, some of these assumptions do not hold true. Okay, so of course we need to then reassess how we're going to make an analysis of the scheduling approach. Okay, so for the first question, we have three periodic tasks, T1, T2, and T3. Okay, where this is the worst case execution time, this is the deadline, and this is the period. Yes, and as you can see, the deadline and the period in this case are basically the same. Okay, and it tells us that uh, this is the worst or the latest time by which I must complete my task, and I'll also repeat uh, or start the next period immediately after that. Okay, so the period and deadline are the same. Okay, the worst case execution time, okay, in this case is the time that the particular task will take, okay, to compute, okay, given its set of activities that it needs to complete. Okay, so the question is asking if there is a feasible schedule. Okay, sorry, the question asking demonstrate that a feasible schedule based on fixed priorities exists. Okay, and basically from what we know from our lecture slides, if there is a feasible schedule, then one of it must be RMS. Okay, so that is what we have understood from lecture slides. Okay, so the RMS scheduling approach, rate monotonic scheduling, basically tells us that if you have fixed priorities and you just randomly try all possible combinations, one of the combinations, if it is possible to schedule them using fixed priority, then one of the possible combinations would definitely be one that satisfies RMS. Okay, so all we need to do is we need to try RMS and see whether RMS actually fulfills the requirements presented here. So in RMS, basically the one with the shortest period is given the highest priority. Okay, so task 1 will be the highest priority, followed by task 3 and the task 2. Okay, so as you can see, task 1 takes 3 units of time over here. Okay, and then task 3 is taking 5 units of time. Okay, but once sorry, after that is task 3 over here taking 4 units of time. So task 3 taking 4 units of time, and once that is done, what happens? Your task 2, so task 1 first, followed by task 3, then followed by task 2. So task 2 is supposed to take 5 units of time. It takes 2 units. Okay, but before you can complete, what happens? The periodic interval of T1 kicks in. Okay, which means the next cycle T2 is preempted and T1 is ready and it takes over the CPU. Okay, so T1 will run, and after T1 runs, then what you have? You have another, okay, iteration of T3. Okay, because T3 is supposed to repeat every 12 cycles. So T1 preempts at cycle 10. It takes 3 clock cycles. So once the 12 cycles are complete, T3 is ready and T3 will be able to run. Correct? So when T3 runs, it will take 4 clock cycles. And what happens is, once T3 is complete, then T2 will be able to resume. Okay, so at this point of time, T3 takes another 4 clock cycles over here. And once T3 takes the 4 clock cycles, we are able to resume, okay, task 2 over here. But as you can see, task 2 has only completed 2 cycles here and another 2 cycles here before it hits the deadline of 18. Okay, so because by the 18th cycle, T2 has only completed 4 cycles, it misses its deadline. Okay, so basically this approach, this question is basically asking us to analyze based on the RMS approach, where the shortest period has the highest priority. Okay, so the moment the periodic interval is up, then the task will repeat itself. Okay, and of course, if a higher priority task is running, it will preempt it. If it is not the highest priority task, then it has to wait. In this second question, we are talking about utilization. The formula for utilization is from our lecture notes here, and it says that U is C over P, where the computation time divided by the period. Okay, and we need to sum up all of it, okay, across all the tasks that we have. Okay, so for this task set, okay, we are given the utilization as 0.975. Okay, and U must be less than or equal to 1, which is a necessary condition. Okay, so necessary does not mean it is sufficient. Necessary means you definitely need this to be true, but just because it's true doesn't mean it is schedulable. Okay, so let's look at the next thing, the utilization bound. If the utilization is less than the utilization bound, okay, then definitely there is no issue. Okay, but in this case, U is greater than the utilization bound, so it means that it still may or may not be schedulable. It still may or may not be schedulable, so we need to go through a more detailed analysis of the sequence of the tasks. Okay, so let's look at the tasks. So you have 3 tasks, T1, T2 and T3, with different computation times and different periods. Okay, at the very first instance, okay, so let's go back and put the priorities. So the shortest period, task 1 is the highest priority, this is the medium priority, and this is the low priority based on RMS. So task 1 will run first. After 2 units of time, it will allow task 2 to run. Okay, so this will be 2 units of time, and this will be 3 units of time. And after that, what will happen? After that, task 3 will run. Okay, but task 3 runs, and task 3 only completes 1 cycle before the next iteration of task 1, because task 1 has a period of 6. So 1 to 6 is the first period, and at time 7 it starts the next iteration of the new cycle. Okay, so task 1 being higher priority preempts task 3 and it runs. Okay, and at the same time, immediately after that, what happens? Task 2 is ready, because task 2's period is 8. So 1 to 8 is task 2, and just after that 8 cycle period is over, task 2 will be ready and task 2 will run. Okay, so task 2 will run. So until now, task 3 has only done 1 cycle. Okay, and it is supposed to do 4 cycles. Okay, but it's only done 1 cycle. Okay, and task 1 has already completed again, and task 2 also has completed. After that, what happens? Your task 3 gets another chance to run. So this is the second one. So this is another one more time here. Okay, so one time here, or 1 unit of time, 1 unit of time, and then again task 1 is ready. Okay, because task 1 period is up, so 1 to 6, 7 to 12. So over here at 13, T1 is ready again. Okay, so T1 runs, and again after T1 runs, then you have one more unit of time over here for T3 to run. Okay, and T3 runs one more unit of time. Okay, but by the time, that is the end of the deadline or the period for task 3. Okay, because deadline of the period for task 3 was 15. So by the end of the 15th cycle, I've only done 1, 2 and 3 units of task 3, whereas task 3 is supposed to have 4 units of computation time before its deadline. Okay, so you can see that it misses its deadline. Okay, so in this example here, what we're trying to show you is that the utilization is less than 1, which is a necessary condition, but it's not sufficient. Okay, but the utilization less than the utilization bound is sufficient. But since we did not fulfill that request, we have to go through this detailed analysis. Okay, and through the detailed analysis, we are able to see that the utilization or the tasks are actually not schedulable under RMS. Okay, so that is basically just to recap some of the concepts of scheduling that we saw in the lecture. In this question, we're going to be looking at mutex. Okay, so for this question, what do you see? You see that this is basically accessing a shared resource, which is the LED. Okay, so this code here, which is accessing the shared resource, okay, has to be protected. Okay, and from what we know from our labs and our lecture slides, we know that in order to protect a shared resource, before I access the shared resource, I must call OS mutex acquire, and after I finish it, I say OS mutex release. Okay, and that is basically so the whole idea of mutex is basically mutual exclusion. That means once I acquire a mutex, if somebody else tries to come in and access the shared resource through the same mutex, they will not be able to do it. Okay, so they will be put on a block state, okay, until the resource is available. Okay, and that is basically what is going to happen here, okay, or in the lab, as what you would have seen. And the main reason why the task waits until the mutex is available is because of this timeout value here, which is OS wait forever. Okay, when we say OS wait forever, we are telling the OS that at this point of time, I'm trying to acquire a mutex. If it is available, good, I'll get it. If it is not available, then I will just wait there forever until it becomes available. Okay, so that ensures that you are able to proceed on with controlling or accessing this shared resource only after getting the mutex. And once I'm done, I release the mutex. So the question now is, what will happen if I change this to 0? Instead of putting a OS wait forever, I say 0. That means I do not want to wait. I do not want to wait. What does that mean? Okay, so let's look at this explanation here. So timeout value of 0, okay, basically means it is a situation where you are not going to wait for the mutex at all. Okay, so if you're not going to wait for the mutex and you're still going to carry on, does it mean you actually got the mutex? No, it doesn't guarantee you that. Okay, so it means that you are still going to proceed on with the rest of the code. So over here, if I change this to 0, I will still proceed on with the rest of the code regardless of whether I got the mutex or not. Okay, so what I need to do is I need to be very careful to know whether did I really get the mutex or I didn't get the mutex. Okay, if I change the timeout to 0. So that is where we need to look at the return values. Okay, so most OS kernel calls have a return value. So in this case, it's OS status T, and basically only the first one says it is okay. Okay, all these four are related to some form of error. Okay, so all we need to do is we need to check that the return value, is it okay or not. Okay, so as long as this return value here is not okay, means something went wrong. Okay, so as long as something went wrong, then I have to have some other code to handle this. Okay, so if I come to this else here, that means I actually acquired the mutex, okay, successfully. Okay, so if I come to this else over here, that means I actually acquired the mutex successfully, so I'm able to control the shared resource. Okay, if the mutex acquire wasn't successful, then the status wouldn't be OS okay. It would have been some other error condition. Then I need to make sure I handle that over here. Okay, so in general, okay, most of the time we prefer to use the wait forever options, okay, because that ensures that you are only proceeding on after you have acquired the resource that you are waiting for. Okay, so that is generally how we use mutex, but you also have the option of not waiting. Okay, then we need to also be careful of how we handle this situation in the code. Okay, so that basically brings us to the end of the tutorial discussion over here. In the next tutorial, we'll be discussing a bit more on the mutex, okay, as well as the semaphores. All right, thank you.